Thank you for the introduction. Good morning, everyone. This is a joint work with Dr. Sudarshan Srinivasan, Sana Sahuja, and Ziad when I was a student at North Dakota State University. The problem that we are looking at in this work is verification of real-time object code programs using refinement checker techniques. Why do we consider this to be an important problem? Safety critical embedded devices like medical devices, surgical robots, avionic control systems, automobiles, nuclear systems, etc., have software as their control program. Ensuring the correctness of these control softwares is still an ongoing challenge. FDA has issued 51 Class 1 recalls from 2001 to 2019 on medical devices due to software errors. Class 1 recalls are applied to medical devices whose use can cause serious health consequences. Recalls are not just applied to medical devices. These embedded devices execute object code, and hence we need to verify the object code that it executes to ensure proper behavior. This is a challenging problem because object code is low level, mostly interrupt driven, which makes the behavior of the code non-deterministic, and real-time object code also has hard real-time constraints that should be met. All of these features together make it a challenging verification problem. The suggested solution is the use of formal verification techniques to ensure the software correctness, which deals with safety critical applications. Formal verification techniques have become a standard in industry like Intel, Microsoft, Airbnb, ARM, etc. Before we dwell into the topic, there are certain terminologies that have to be understood. I will go over each of them now. The first one being transition system. A transition system, TS, is a triplet which consists of S, R, and L, where S is the set of states, R is a transition relation that defines the state transitions, L is a labeling function that defines what is visible at each state. For example, in the figure that is shown, the set of states S are S0, S1, S2, and S3. The transition relationship is shown by the arrows, which is S0 to S1, S1 to S2, S2 to S3. What does this S0 means to the world is known through the application of the labeling function L. The next terminology is a specification transition system. In general, any application before it's being developed has to be described as to what it has to do, how it has to do, and things of that kind. And usually these are written in English, in a language that is understood by humans. This requirements have to be taken and then translated into a transition system, which then acts as a specification transition system. This is used as a reference to our software program. Here we are going to use the example of stepper motor, which is basically an electric motor. It is used widely in many applications. Its main feature is that it allows for precise motion control. So it is used wherever we need precise motion control, like medical devices, surgical robots, process control, etc. There are many safety critical applications of stepper motor, and the number of applications continue to grow. Stepper motor has 4 or 6 leads on which a sequence of values like 0001, 0010, 0100, 1000, 0001 causes the motor to rotate. Every time we switch to the next value in the sequence, the motor rotates by a small angle. For example, when we switch from 0001 to 0010, the motor rotates, and then from 0010 to 0100 again, it rotates, and so on. By giving this repeated sequence continuously, the motor rotates. Hence, this behavior can be achieved by using a microcontroller to control the motor. Here, I express the motor control as a transition system. There are many applications for which the control can be expressed as a transition system, and our approach works well with all of these applications. what is an implementation transition system? When this simple behavior of stepper motor is written on a microcontroller, the source code is compiled and translated to object code. A single line of object code translates to a single line of source code translates to one line of to more than one line of code and in the object code. So this low level language is what needs to be translated to a transition system, which is known as our implementation transition system. This is an example of an object code transition system for stepper motor. Different type of applications would have different type of implementation transition systems depending on what the source code is. And now we have two systems expressed as transition systems. One is specification and the other is the implementation. How can we compare this? In formal verification, refinement-based techniques have been demonstrated to be applied to the verification of embedded software control at the object code level. Also, it involves transition systems to represent the model. Our notion of refinement is based on the theory of WFS refinement, which tells you what it means for two transition systems to be functionally the same. WFS refinement stands for well-founded simulation refinement, and it has some unique techniques, unique features. The first feature in the content of WFS refinement is specification, which is a transition system, as opposed to property checking, where specification is a property in temporal logic. For many applications, it is possible for encoding the behavior as a simple transition system. The specification model captures the correct functionality of the system. The next feature of WFS refinement is the use of refinement map. The design artifact to be verified is called the implementation model. The verification problem reduces to refinement checking problem, where we check if the implementation transition system is the WFS refinement of specification transition system. When we look at these transition systems, there are many differences. The first difference is that the implementation transition system has many more transitions than the specification transition systems. Object code is primarily executed on microcontrollers. So if we look at the state of the implementation, it has registers, memory, special control registers, flags, etc. It looks very different from our specification, which has only 4 bits. Refinement map is a function that allows to bridge this abstraction gap. Hence, given an implementation state, it tells what the corresponding specification state looks like. For this example of stepper motor, refinement map function is projecting the bits of the register which holds these 4 values that is connected to the leads. So applying the refinement map function to the implementation transition system gives us the state in red match to S0, green match to S1, yellow match to S2, orange match to H3, and brown match to S4. For example, if we take state 6, in the implementation, we know it matches to S1. The third idea is stuttering. Stuttering is the idea that multiple but finite steps of implementation can match to a single step of specification. So for example, if we look here, state 20 corresponds to S2, which goes to S3, which is state 21. For the implementation to go from S1 to S2, it doesn't happen right away. It takes several steps and has multiple paths. If you look at this path, it takes several steps that are finite in number before it makes this transition. On the implementation side, the steps that map to the same specification are known as stuttering steps, like state 4 to state 5, whereas the transition between state 2 to state 3 is a non-stuttering step. Stuttering is a key concept because it allows to check equivalence between implementation and specification, where there's a lot of stuttering on implementation side. Especially for real-time object code, the code is often going through a loop waiting for some counter to get updated to a specific value. Here the code is strictly doing a lot of stuttering. Let us take the example where we go from 2 to 3. This corresponds to S0 to S1. On the implementation side, this transition doesn't take place right away. Consider one of the paths which is outlined here. The idea is simple. This has reached state S1 at 3 and moves to state S2 at 13. We call this a stuttering segment. A stuttering segment has finite steps where the first transition is a non-stuttering step, the last transition also a non-stuttering step, and everything in between are stuttering steps. Here, 3 to 12 is a stuttering segment which is preceded by a non-stuttering step. We want this for S1 to S2 transition on specification, we have 3 stuttering segments on the implementation transition system, which is shown here. Applying certain kind of techniques, these stuttering segments can be reduced in length, but we have not described these techniques in this paper because that's not the main point. There has been a lot of previous work in developing theory and optimized techniques for refinement-based verification. A notion of refinement based on stuttering trace containment to verify concurrent programs have been developed by Ray and Summers. A refinement-based testing method has been developed by Jane and Manolis, which checks for functional correctness of hardware and low-level software. An algorithm that checks equivalence between two transition systems which account for stuttering has been presented by Groot and Witz. However, these do not consider real-time interrupt-driven object code. In this work, we use WFS refinement, which has a very nice property. The check is local, that is, it is sufficient to reason about one step of implementation and specification. Since object code typically contains millions of transitions, this property can be exploited by reasoning about one transition at a time. This in turn reduces the verification burden. Jabin et al. Have used the theory of refinement for verification of FPGA-based stepper motor control using proof obligations. Manually developing proof obligations for real-time interrupt-driven object code is time-consuming because of the size of the instructions and may introduce human errors. In contrast, we address the automation of refinement-based verification. Automation helps in verification of large-scale programs. The proposed methodology checks for correctness property which are captured through safety. Safety informally means that if the implementation makes progress, the result of that progress satisfies the specification requirements. The formula to check WFS refinement is expressible in a desirable fragment of first-order logic. Once we have transition systems of the implementation and specification, we can check WFS refinement using a decision procedure. Consider a state W in implementation transition system, a state S, which is the refinement map of W in the specification transition system, such that V is the successor step of W, U is the successor step of S. Then for all W in implementation transition system, they exist U, which is a refinement map of V in case of non-stuttering step, or S, which is the refinement map of V in case of stuttering step. Uh, for this work, the implementation transition that is considered is shown on left, but we have not directly considered this implementation transition system. We have applied some abstraction techniques and obtained the transition system on the right. This is the example that I'm going to use for describing the algorithm that we have proposed. Before we dwell into the algorithm, there are certain terminologies, certain things that have to be known again. RI, which is the abstracted implementation model as shown on the left. RS is the specification model. SS is a set of specification states. R is a refinement map function. RU is the counter set example. W is the current implementation state. V is the successor implementation state. S is the current specification state. U is the successor specification state. Match is a flag which can take a value of 0 or 1. Modulus of Ri is the total number of transitions in implementation model. Modulus of Rs is the total number of transitions in specification model. So using the specification on the left and the implementation on the right, we initialize these variables to SS, which contains the set of state of specification, which is S0, S1, S2, S3, and S4. RU, the counter example set, is null. W, V, S, U are all assigned to null. Match, which contains the Boolean value, is assigned to false. And this implementation transition system on the right has 24 transitions, and the specification transition system has 5 transitions. So once we have initialized the variables, we start with line 3, where I gets the value 1, and it goes all the way up till 24. We have to consider W comma V from our implementation transition system. So W and V get the value of the first transition, which is 1 goes to 2. Line 5 says that S should get the value of R of W, which is the refinement map of W. And we know that since it is in red, that corresponds to S0. We are just ensuring that match is initially false. Now we check if S belongs to the set of states of specification, and here S is S0, which is part of the set of states. So this if condition is satisfied. We go to the if condition in line number 8. We check if R of V is equal to R of W. Since 1 and 2 are represented in red, which belongs to the same set of states, the if condition is satisfied and the match value is changed to true. The value of I is incremented, and we look at our second transition, which is 2, 3. So W and V gets the value 2, 3. Now the refinement map of 2 is still S0. So S gets the value S0. Match is changed to false. The if condition on line 7, where S0 belongs to a set of states of specification, is true. Going to line 8, we check if the refinement map of V is equal to the refinement map of W. From the figure, 2 belongs to S0, 2 and 3 have different colors, which means they belong to different states. So this if condition is false. So it goes to the else part. Here J is initialized to 1. The states corresponding to S0 is going to S1. So S and U gets the value S1. Now we check if the refinement map of V corresponds to U. Here the refinement map of U is in green and S1 is in green. So there is a match. Match value changes to true. We come out of the for loop and we go to the line 16, where if match is false, here this if condition fails. So we go back to the for loop where the value of I is incremented. So we go through each transition in the implementation. We go through each of those transitions, and if any of these if condition number 16 is not satisfied, if the condition in line 16 is not satisfied, we collect those transitions into a set called RU. When we finish checking for the entire implementation, the RU value is returned to the user. If there are no bugs in the system, RU is empty, which means there are no counterexamples, and both the implementation and specification transition system match each other. In case the implementation transition system doesn't match the specification transition system, we get the set of transitions that are not satisfying the specification in our counterexample set RU. For this paper, we have considered two different case studies. The first one is the stepper motor. We've used three kinds of controls for the stepper motor: full stepping, half stepping, and double stepping. And we also divided these stepper motor controls into two, which is interrupt driven object code and non-interrupt driven object code. For the interrupt driven object code, we have used RIT timer, which is repetitive interrupt timer, which keep track of the time delay and generates an interrupt when the delay is reached. The motor is updated to change its states at this time. And the second case study that we have used is an infusion pump controller. An infusion pump is a medical device that is used to deliver controlled doses of medication or nutrients into the patient's circulatory system intravenously. Typical medication delivered include opioids, insulin, chemotherapy drugs, etc. The criticality of the pump's functionality is because if it delivers an incorrect dosage due to a software error, it could lead to patient's death. We have used IARIA's 8100 LPV module infusion pump for our experiments. The IARIA's Medley pump uses pulse width modulation for dosage control. We implemented the pulse width modulation control for IARIA's pump on an ARM Cortex-M3 based LPC 1768 microcontroller, which was interfaced with the pump so that the code implementation can control the pump. We have also taken the formal specifications for the pump control software based on requirements from another paper that has been published. These are our verification results for case study 1, which is the stepper motor. This table gives statistics for the correct and buggy version of the controller. Func bug indicates that the object code has an error, which is a functional error. The programs were developed to run on an ARM Cortex-M3 based NXP LPC 1768 microcontroller. Stepper motor leads were connected to 4 pins from port 2 of the LPC 1768 via an electronic circuit. As you can see, the stepper motor controller has from 2.5 million to 148.5 million transitions in it. Using the implementation transition system and applying the refinement checker techniques would take a lot of time. Hence, these benchmarks have hence on these implementation transition systems, we have applied suitable abstraction and reduced the size and then applied the refinement checker on it. In this way, the time for WFS verification is in microseconds. The table here shows the verification statistics for the infusion pump control case study. The transition system of the pump's control code has about 24.3 million transitions. With the application of suitable abstraction techniques, the abstract transition system is obtained and WFS refinement verification was completed within few milliseconds. Here also we have shown if there was a bug present in the control in the pump's control program, you can still find out that the time it has taken to show the buggy model is still very less, which is in milliseconds. So given a specification as a transition system and its low-level object code, WFS refinement could be verified using this automated tool. The automated tool gives better performance when we use the abstracted implementation transition system. Having automated verification tools can be applied multiple times throughout the verifications, throughout the various stages of software development. Future directions. So we have used the automated WFS refinement tool to check only for the safety feature, but sometimes the control software could have other kind of bugs like deadlock bugs. So it is intended to extend this work for checking for liveness, which is checking for deadlocks. So the reason why I've used this particular abstracted implemented transition system is that we can show the bugs where once the controller goes from 27 to 35, it could always keep rotating between 35 and 37, or it could just be stuck at 27 and never go back to state 3. So these are bugs that have to be found, which would put the software in a buggy state. Thank you. If you have any questions, please reach me at my email address and I'll try to get back to you.